Good morning, one and all. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in today's lecture, what we are going to learn is polarization of uniform or plane waves in electromagnetic waves and transmission lines. Right? So the polarization of uniform plane waves. So the name itself tells us that polarization means orientation of electric field in the direction of, depending upon the directions, different types of polarizations are there. Now in this particular, what do you mean by polarization of uniform plane waves, how these two are formed, and how many types of polarizations are there, that and all we will learn in this particular lecture, right? So before going to discuss about this polarization of uniform plane waves, first let me introduce about surface impedance of a good conductor, right? So what do you mean by surface impedance first? How it is related to characteristic impedance, right? So, or intrinsic impedance of the good conducting medium. How these two are related internally means with the help of the surface impedance we will relate the two relations. Nothing but surface impedance and intrinsic impedance. Okay. So firstly, definition of a surface impedance. The ratio of tangential component of electric field. Tangential component of electric field means we are representing it with ET. Means electric field intensity is generally denoted with E, and tangential component means we are representing it with ET, right? And similarly, normal components means we will consider the notation for that is EN, right? So as we have discussed these two components in the boundary conditions between homogeneous and isotropic medium case, right? So where the total electric field E is decomposed into two orthogonal components, one is tangential component and another one will be normal component, right? So these two are orthogonal to each other, means the angle between two are exactly differed by 90 degrees, right? So the ratio of tangential component of electric field to the surface current density at the conductor surface. Okay. Surface current density. Generally we use the notation for current density as J, and here it will be surface current density, means we are representing it with surface current density as Js, right? So surface impedance can be generally defined as it is the ratio of the tangential component of electric field intensity vector to the surface current density at the conductor surface. Okay. So we are considering here the medium is related to conducting medium. As we know that for an ideal conductor, the conductivity value sigma equal to infinity, and according to that Jc means conduction current density is given by Jc equal to sigma into E, where sigma be the conductivity of that medium and E be the applied electric field. Okay, so where Jc is nothing but conduction current density. Why we have considered this conduction current density means we are defining the surface impedance with respect to the conducting medium, right? That's why in general this surface impedance, generally we use the notation for impedance means Z, and S stands for here surface. Hence the notation for surface impedance is represented with Zs, and it is the ratio of tangential component of the electric field intensity E to the surface current density of the conductor surface. So mathematically we can write the equation for that is Zs is equal to E tan by Js, where E tan is nothing but tangential component of the electric field intensity and Js is nothing but surface current density. To derive the relation between the surface impedance and intrinsic impedance, we will consider this as the first fundamental equation, hence it will be applied it as equation number 1. Next, with the surface at z is equal to 0 plane. So at z is equal to 0 plane means which plane we are supposed to consider? XY plane, right? So planes how we are going to identify means x is equal to 0 plane, or it is also called as YZ plane. Y equal to 0 plane, or it is also called as XZ plane. Similarly, if z is equal to 0 means XY plane we have to consider. So with the surface at z is equal to 0 plane, then the current distribution in z direction is given by, right? So J is equal to, so this current density J can be expressed in terms of its magnitude and phase functions, means J is equal to J naught into e power minus gamma z, where J naught is the magnitude of this current density and e power minus gamma z is nothing but phase function for that respective J. Gamma is nothing but here propagation constant and z be the direction of that wave. Okay, so J can be given by here J naught into e power minus gamma z. Then consider this as another equation and equation number 2. So already we have in the equation number 1 what we have, Zs is equal to E tan by Js, and here J equal to J naught into e power minus gamma z, right? So from these two equations we are going to derive the relation. Then the linear current density is given by, so as we know that Js is the surface current density, now in order to derive that equation we just integrate that one with respect to the function as Js is equal to integral 0 to infinity J naught into e power minus gamma z dz. So why we have considered the limits as 0 to infinite means we are considering here J equal to J naught into e power minus gamma z means forward direction wave propagation term we have considered. Forward direction means the range means how it will be represented. The path the field is ranging from 0 to infinite region. Suppose if we consider backward direction wave, then the limits will be becoming then minus infinity to 0. So now we have here forward direction wave means the ranges of that integration limits will be considered as integral 0 to infinity, as lower limit as 0 and upper limit as infinite. Then substitute in place of J by J naught into e power minus gamma z dz. Okay, so now if we are integrating this one, Js is equal to integral 0 to infinity J naught into e power minus gamma z into dz. We are integrating this one with respect to z, right? Hence J naught can be treated to as a constant, then J naught integral 0 to infinity e power minus gamma z into dz. Now after integration means J naught is a constant, then integration of e power minus gamma z resultant will be e power minus gamma z by minus gamma. Then if we substitute limits as 0 to infinity, right? So J naught into e power minus infinity by minus gamma minus of e power minus gamma z, nothing but 0 e power minus 0 by minus gamma. Okay, so this becomes 0 and the J naught into minus of this minus becomes plus, e power 0 as 1, then 1 by gamma is left out. Then Js is obtained as J naught by gamma. Okay, so this we have written as Js, surface current density Js is equal to J naught by gamma, as we have integrated that with respect to the 0 to infinity range. Okay, then but we know that J naught means according to the conducting medium, according to the conduction current density, that J naught is given by sigma into E tan, right? sigma conductivity of the medium and tangential component of the electric field intensity, right? So just substitute in place of this J naught by this relation, sigma into E tan. Okay, then Js is equal to J naught means sigma into E tan by gamma, right? Then Zs is equal to gamma by sigma, means Js is equal to sigma into E tan by gamma as we obtain from this linear current density. Then from the definition of this surface impedance, that is given by what Zs is equal to E tan by Js. What is Js here? From this relation, E tan by Js is nothing but sigma into E tan by gamma. Okay, so this E tan gets cancelled, gamma by sigma is obtained from this relation. Okay, so from this surface impedance, then we have got the relation as Zs is equal to gamma as propagation constant to the conductivity of the medium Zs. Okay, from the relation of linear current density, Js value is obtained J naught by gamma, and if we substitute J naught by conduction current density, then the formula is given by sigma into Et, and if we substitute in place of J naught by the sigma into E tan in this particular, and from that surface current density fundamental definition, then Zs is given by here gamma by sigma. Okay, then now to relate the surface impedance and intrinsic impedance, that is eta. So first, from the characteristic means propagation characteristics equation, the propagation constant gamma is given by. So according to the propagation characteristics of the medium, here we have considered the gamma means propagation constant gamma is given by root over j omega mu into sigma plus j omega epsilon. So what is that condition for good conducting medium? As we know that sigma by omega epsilon is far greater than that of 1, or sigma is far greater than that of omega epsilon, right? So if you, in order to satisfy or in order to act as a good conducting medium, it must satisfy the condition that sigma by omega epsilon is far greater than that of 1, or sigma is far greater than that of the omega epsilon. Means at high conductivity case, at low frequencies case, medium behaves as good conducting medium, right? So now according to the conducting medium, if we substitute in place of this sigma plus j omega epsilon this condition, then j omega epsilon might be is very less when compared to the sigma, hence we can neglect this omega epsilon. Then root over term becomes gamma equal to root over j omega mu into sigma. Okay, then Zs is equal to, so previous from linear current density, what we have got, Zs is nothing but gamma by sigma, right? Now from this propagation characteristics, gamma is to be obtained as gamma equal to root over j omega mu into sigma, right? So now substitute in place of this gamma by that relation, means root over j omega mu into sigma by sigma. Okay, which is equal to, this can be written as j omega mu into sigma by, if you take this sigma into inside the root, then it becomes sigma square. This sigma and this square gets cancelled. Zs is equal to root over j omega mu by sigma. So for a good conductor, that intrinsic impedance is eta is given by root over j omega mu by sigma according to the propagation characteristics of a good conducting medium, right? So from this relation we can say that surface impedance of the good conducting medium is similar to that of intrinsic impedance of the good conducting medium, right? And from that mathematically we can write Zs is equal to eta equal to root over j omega mu by sigma, right? See here, if you observe gamma from the characteristics, propagation characteristics, that equation is obtained root over j omega mu into sigma, and Zs is equal to root over j omega mu sigma by sigma. Why we have substituted means from the previous analysis from the linear current density, that surface impedance Zs is obtained as by gamma by sigma, right? If you substitute gamma by that relation, root over j omega mu into sigma by sigma, which is equal to, then here if you observe in the numerator that sigma is in the inside the root, and in the denominator the sigma is exist out of that root. If you take this sigma into inside the root, then it becomes sigma square, then square root gets cancelled, it remains the previous statement. And to cancel these two, sigma square and sigma, then it becomes Zs is equal to root over j omega mu by sigma. And since it is we know that intrinsic impedance of the good conducting medium eta equal to root over j omega mu by sigma, right? So from these two relations we can say that, what we can say that for a good conductor, the surface impedance of a plane conductor with a thickness greater than the skin depth of a conductor is equal to the characteristic impedance of the conductor. Or in simple words we can say that for a good conducting medium, surface impedance is similar to that of intrinsic impedance of the good conducting medium. And mathematically we can write Zs is equal to eta is equal to root over j omega mu by sigma. Okay, so in general how we can define the surface impedance means Zs is nothing but it is the ratio of the surface impedance of the good conducting medium can be defined. It is the ratio of the tangential component of electric field intensity vector E tan to the surface current density as J, well, if you consider conducting medium, conducting surface. Hence, Zs is equal to E tan by Js. Now, in order to get this relation, Zs means surface impedance and intrinsic impedance, we will consider linear current density integration. Then from that, Zs is to be obtained as Zs equal to gamma by sigma. Now from the propagation characteristics, as we know that gamma equal to root over j omega mu into sigma plus j omega epsilon. Now from the conducting medium condition, sigma is far greater than that of omega epsilon case. If we neglect this omega epsilon, then we will consider only sigma. Then that is the case, sigma is to be obtained, means propagation constant gamma is to be obtained as root over j omega mu sigma. And if we substitute this gamma by this relation j omega mu into sigma, then Zs is to be obtained as root over j omega mu by sigma, right? And it is nothing but intrinsic impedance of the good conducting medium, right? So for a good conductor, the surface impedance of a plane conductor with thickness greater than the skin depth of a good conductor is equal to the characteristic impedance of the conductor, right? So this is the way we can write the general definition for the surface impedance, and mathematically we can write that equation as Zs is equal to E tan by Js, which is nothing but root over j omega mu by sigma, and it is equal to eta. Okay, so this is about surface impedance of a good conductor. Next, so from this we can say that Zs is equal to eta, right? Surface impedance is nothing but intrinsic impedance of a good conductor. Okay, then polarization of uniform plane waves. Okay, so firstly, what do you mean by polarization? Now, how many types of polarizations are exist? How we can relate linear polarization given the wave is said to be, when the wave is said to be linearly polarized, and when the wave is said to be elliptically polarized, and when the wave is said to be circularly polarized. Okay, so depending upon this, we will define firstly polarization of uniform plane waves, then we will go for in detail analysis of linear polarizations, different types of the polarizations. Okay, so first definition: the polarization of a plane wave, polarization of a plane wave can be defined as the orientation of electric field vector as a function of time at a fixed point in particular in a space. Okay, so polarization of a uniform plane wave can be defined as the orientation of electric field vector as a function of time at a fixed point in the space. Okay, so for an electromagnetic wave, where uniform plane wave is nothing but electromagnetic wave, and for an electromagnetic wave, the specification of orientation of the electric field is sufficient as the magnetic field components are related to the electric field vector by the Maxwell's equations. Okay, so in the why we have considered only electric orientation of the electric field vector only means if you define electric field component from the Maxwell's equations, we are also relate that equation with respect to the magnetic fields. That's why we have considered specifically only the orientation of electric field. Okay, so for an electromagnetic wave, the specification of the orientation of the electric field is sufficient as the magnetic field components are related to the electric field vector by the Maxwell's equations. As we know that there are two Maxwell's equations in the time varying fields which gives the relation between electric field vectors and the magnetic field vectors. According to the Faraday's law, that is del cross E bar equal to minus dou B bar by dou T or minus mu into dou H bar by dou T, where E bar is given by the electric field intensity vector and H bar is the magnetic field intensity vector. And as we know that V bar is nothing but magnetic flux density, and it is the relation between flux and field intensity is given by B equal to mu into H. If you derive the equation E, then it is automatically derived the relation for H also. That's why in the polarization case we used to consider only the orientation of the electric field is enough. Okay. Similarly, one more Maxwell's equation relation between electric as well as magnetic fields or del cross H bar equal to J plus JD, where J is nothing but conduction current density and it is given by sigma into E plus JD is dou D bar by dou T, and D bar is given by epsilon into E. Then if we substitute here sigma into E plus epsilon into dou E bar by dou T. Okay, so from these two also, if you derive the equation for H, automatically we will get the equation for E also. Okay, then then we will consider these two Maxwell's equations in order to get the relation between electric as well as magnetic fields. Okay, then for an electromagnetic means, from the definition of a polarization of uniform plane waves, firstly the polarization of a uniform plane wave can be defined as the orientation of the electric field vector as a function of time at a fixed point in space. Okay, then for an electromagnetic wave, the specification of the orientation of electric field is sufficient as that magnetic field components are related to the electric field vectors by the Maxwell's equations. Right? So that's why in the polarization case we just consider only the orientation of electric field vector is enough. Okay. Then types. How many types of polarizations are there? So three cases of polarizations we have: linear polarization, elliptical polarization and circular polarization. Linear case only one directional element we just consider, and in the elliptical as well as circular polarizations case two direction rotation we are going to consider. Okay, so there are three types of polarizations are there: linear polarization, elliptical polarization and circular polarization. Okay, now polarization Or in other words, we can define the polarization as the polarization is a property applying to transverse waves. Transverse waves means electromagnetic waves in general. So polarization is a property applying to transverse waves that specifies the geometrical orientation of the oscillations. Right? Orientations means rotations of geometrical orientation of the oscillations or specifies the polarization of transverse waves. Okay, so polarization is a property that applying to transverse waves that specifies the geometrical orientation of the oscillations. Okay, then in linear polarization, in circular polarization, and in the elliptical polarization, how the orientation will be, right? So in a linear polarization, the fields oscillate in a single direction, as we know that linearly varies. So in general, line equation we have to consider y equal to mx plus c. If you keep on increasing the value of y, automatically x is also to be increased, linear increasing, right? That's why only one direction rotation we have to consider. So in linear polarization, the fields oscillate in a single direction. And in the circular or elliptical polarization, the fields rotate at a constant rate in a plane as the wave travels. Okay. So in the single direction of linear polarization means either x direction or y direction. Right? Suppose if we are assuming the direction with respect to x, y will be a constant. Suppose if we are rotating with respect to y, x will be a constant. That's why in linear polarization, the fields oscillate in a single direction, whereas in the circular or elliptical polarization, the fields rotate at a constant rate in a plane as the wave travels. Okay, then actually linear and circular polarizations are special cases of elliptical polarizations, right? So remember this point, very important, that is linear and circular polarizations are special cases of the elliptical polarization. So how we define polarization? It is the orientation of the electric field at a particular point in a space, or geometrical variations of the oscillations is nothing but polarization. And basically there are three types of polarizations or occur: linear polarization, elliptical polarization, and circular polarization. Okay, now individually how we are going to define this linear polarization, how we are going to identify. Given one is elliptical polarization and circular polarization. Okay, so polarization first. Three images. In the linear polarization case, direction will be considered for only one direction, whether it is x direction or y direction. That's why the field components or the wave will be rotating as like this. In the circular and elliptical, two directions we are supposed to consider, hence e direction as well as ex direction. If you consider, one is ex direction and the other one will be y direction. Similarly, in the elliptical case also, if we are assuming one will be in x and the other will be in y. Okay, and depending upon the amplitudes and the phase angles, these two are different: circular polarization and elliptical polarization. See, if you observe, linear means only one direction, and circular elliptical case, two directions we have to consider. And if you observe, the magnitudes of these two are exactly equal, means ex magnitude and ey magnitude must be equal, and the phase angle between these two are exactly equal to 90 degree case. The wave is said to be circular polarization. And here if you observe, see, this is the direction, means magnitude of this and this will not be exactly equal to same, and the angle between this is less than that of 90. Case, the polarization is said to be elliptical polarization. Okay, so now then linear polarization first. Three types of polarizations are there. First case is linear polarization. In the linear polarization case, how the wave is to be rotated, then how we are going to represent it in the graphical manner. So see, the electric field E has only X component. If the electric field E, electric field notation generally we used to consider as E. So the electric field E has only X component and Y component of E is 0. As we said in the previous case, linear polarization is to be considered only one particular direction. Means if you are assuming it with X direction, the other direction means Y direction will be, component will be equal to 0. Suppose if the orientation is with respect to Y, X component will be equal to 0. That we need to remember carefully. So the electric field E has only X component and Y component of E is 0. Right? So electric component E has only X component, EX component only, and Y component of that will be equal to 0. Then the wave is said to be linearly polarized in which direction? X direction. X direction. Right? Suppose if the electric field E has Y component and the X component of that will be equal to 0, then the wave is said to be linearly polarized in Y direction. Linearly polarized in Y direction. Okay, this is the way we can define linear polarization. So the electric field E has only X component and Y component of E is 0, then the wave is said to be linearly polarized in the X direction. And or we can say that in other direction as if the electric field has only Y component and X component of that is 0, then the wave is said to be linearly polarized in the Y direction. Okay? Or in other words, how we can define this linear polarization? Means the resultant vector E is oriented in a direction which is constant with the time and the wave is said to be linearly polarized. Means the resultant vector E is oriented in a direction which is constant with the time and the wave is said to be linearly polarized. This is the way also we can define linear polarization. Or in short, by combining these two, we can define EX and EY components are in phase. Means exactly same, no? Then the angle between two is exactly equal to 0 degrees. EX and EY components are in phase means two are differ by 0 degrees phase. EX and EY components are in phase with either equal or unequal amplitudes. Means that wave must be having equal amplitude or else unequal amplitudes. For a uniform plane wave traveling in Z direction, the wave is said to be linearly polarized, or the polarization is linear type. Okay, so we are representing it with E0 components are E0x and E0y. Suppose firstly how we are going to define? If the electric field E has E0x component and Y component of that is 0, means E0y is equal to 0, then the wave is said to be linearly polarized in the X direction. And suppose if the electric field E has Y component means E0y and the X component of that is equal to 0, E0x is equal to 0, then the wave is said to be linearly polarized in the Y direction. Or if Ex, both the direction components, both the magnitudes if you consider E0x and E0y, means Ex and Ey components are in phase 0 degrees between two and with either equal or unequal amplitudes of the wave for a uniform plane wave traveling in Z direction, then the polarization is said to be linear polarization, or the wave is said to be linearly polarized in that particular direction, either X direction or Y direction, not exactly both. Okay, then second type of polarization is elliptical polarization. As we know that elliptical shape will be, suppose if you have E0x component, E0y component and elliptically these two are different, elliptical shape, right? So suppose if you observe direction of magnitudes of these two same, length will be not exactly equal to same, and the angle between these two is not exactly equal to 90 degrees. Okay, so based upon this we can define this elliptical polarization as if the electric field E has both the components. Why? Because in the elliptical polarization and the circular polarization we need to consider two directions, hence two components. So the electric field E has both the components which are not having same amplitudes. Electric field E has both the components which are not having the same amplitudes, means E0x is not equal to E0y. Okay, the electric field E has both the components which are not having same amplitudes and are not in phase, means the angle between two is exactly not equal to 0 degrees. That should be more than 0 degrees or less than 90 degrees. The amplitudes of Ex and Ey are different, means not same, and the phase difference between the two is other than 90 degrees. There must be some phase, and that should be less than that of 90, other than that of 90 degrees. If it is less or more, less than 90 or greater than 90, then the axis of the ellipse are inclined at an angle theta with a coordinate axis. This theta should be less than 90 or greater than 90 case the wave is said to be elliptically polarized. Okay, so in brief we will define this elliptical polarization as the components Ex and Ey of unequal amplitudes, means E0x is not equal to E0y, have a constant and non-zero phase difference between two, then for a uniform plane wave traveling in z direction, the wave is said to be elliptically polarized, or simply the polarization is a type of elliptical. Okay, so in order to define this elliptical polarization, two direction components we have to consider, that is the electric field E has both the components which are not having the same amplitudes and are not in phase, or in other words we can define the amplitudes of Ex and Ey are different in the phase difference between the two is other than 90 degrees, then the axis of the ellipse are inclined at an angle theta with the coordinate axis. So by combining these two statements we can conclude the components of Ex and Ey, or in general E0x and E0y of unequal amplitudes, have a constant non-zero phase difference between two for a uniform plane wave traveling in the z direction, then the polarization is elliptical polarization. Okay, so third type of polarization is circular polarization. So by combining those two, means the amplitudes of Ex and Ey. Now to define this circular polarization we need to consider two magnitude terms as E0x and E0y. So but if you compare the directions, means the length of these two will be, or the magnitudes of those two will be exactly same, and the angle between two is exactly 90 degrees case, then the wave is said to be circularly polarized, right? So the amplitudes of Ex and Ey are same and the phase difference between the two is exactly 90 degrees, then the wave is said to be circularly polarized. Means in one wavelength span the resultant vector E completes one cycle of rotation. Such a wave is said to be circularly polarized. Means if one wavelength of span means total rotation, the resultant vector E completes one cycle of rotation, such a wave is particularly said to be circularly polarized in those two directions. Okay, so orientation of electric field vector at a particular time in a space is defined by polarization of the uniform plane wave, and there are three cases of polarizations: linear polarization, and second case is elliptical polarization, elliptical polarization, and third case is circular polarization, right? So how we have defined the linear polarization means, suppose if the electric field component E has X component and the Y component of it will be equal to 0, then simply the wave is said to be linearly polarized in the X direction. Or in other words, if the electric field component E has only Y component and the X component of it will be equal to 0, then the wave is said to be linearly polarized in the Y direction. Means, not to consider that linear polarization, we will consider only single direction orientation with respect to only one particular direction. Okay. Second type is elliptical polarization. So now to define this elliptical polarization, we have to consider two directions must. Means Ex component and Ey component must be there, and the magnitudes of these two are not exactly equal to the same, and phase difference between these two is not exactly equal to 90 degrees. Means that is less than 90 or greater than 90 case, if the electric field has Ex component and Ey component are having this non-same magnitudes are not same, and the angle between two is not exactly equal to 90 degrees, that should be less than that of 90 degrees or more than that of 90 degrees case, then the wave is said to be elliptically polarized. Okay. And circular polarization. So circular polarization case, if the magnitudes or amplitudes of the Ex and Ey are the same and the phase difference between these two is exactly equal to Ex is equal to Ey and the angle between these two is exactly equal to 90 degrees case, then the wave is said to be circularly polarized. Okay. So this is the way we can define three types of polarizations as linear, circular and elliptical. Whereas this linear and circular polarizations are special cases of this elliptical polarization. Sometimes it may follow the linear polarization and sometimes it may follow the circular polarization, right? So polarizations are of three types: linear, circular and elliptical. So here the direction is considered with respect to either X direction or Y direction, but here these two magnitude directions we have to consider. Here Ex is not equal to Ey and the angle is less than 90 case or greater than 90 case. Here the angle is 0 degrees phase shift. Why? Because we have considered only one direction component. Here two directions we have to consider and the angle between two is non-zero phase difference, means that should be not exactly equal to 0 and not exactly equal to 90 degrees case, means less than 90 and greater than 90. This is elliptical. Ex is equal to, this is related to circular, means both the magnitudes are same. Ex is equal to Ey and the angle is exactly equal to 90 degrees case, then the polarization is said to be circular polarization. If you come here, observe elliptical polarization, Ex and Ey are not same and the angle is less than that of 90 or greater than that of 90 case, then the wave is said to be elliptically polarized. Okay. So what we have learnt in this particular lecture is firstly we have defined surface impedance. Now from that we have derived the relation between surface impedance and the intrinsic impedance, that should be equal to root over j omega mu by sigma. These are obtained from the propagation characteristics of the good conducting medium, where Zs is nothing but surface impedance and eta be the intrinsic impedance of the medium. Now we have learnt definition of a polarization. After that we have observed three cases of polarizations as linear polarization, elliptical polarization and circular polarization. So from this polarization we can conclude here the linear and circular polarizations are special cases of the elliptical polarizations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.